All right, today is day 2 of section 2.2, and we are focusing on finishing up stuff that we need to know about a normal distribution or a normal density curve. A couple quick reminders before we dive into this. A density curve is any curve that's at or above the x-axis whose area under the curve is 1. We did a couple of examples of some generic density curves yesterday, one of them being a uniform distribution where we just get a simple rectangle and then a minor variation off of that. And then we went into a specific density curve that's pretty important to us, and that's the normal curve. When you have a normal distribution, one thing that's true, regardless of the particular mean and standard deviation, is the 68, 95, 99.7 rule. That's what your book refers to it as. It's very often referred to in many textbooks and websites as the empirical rule. That's a whole lot easier to say. I'm going to call it this as opposed to that. Okay, by this rule, approximately 68% of the data is within one standard deviation of the mean. Approximately 95% of the data is within 2 standard deviations of the mean. 99.7% of the data is within 3 standard deviations of the mean. And that leaves a mere 0.15% on each tail, more than 3 standard deviations away from the mean. All right, the first example for today, it says a certain standardized test is normally distributed with a mean of 300 and a standard deviation of 25. Use the empirical rule to determine a percentage of students who scored between 275 and 350 on this test. So what I'm going to do, broke the pencil point, sketch a normal curve. I'm going to mark off 3 standard deviations away from the mean in each direction. The mean for this problem is 300. If the standard deviation is 25, then that makes this 325, 350, 375, broken pencil point, 275, 250, 225. We want to know what the probability is, or what percentage of the student, rather, scored between 275 and 350. Well, 275 and 350 would be this area right here. Oops, no, that area too. Going to go all the way to there. So, referring back to one of the slides from yesterday, which I had here a second ago. Apologize, it was in a pile, it's now not here. Here we go. Yesterday we finished up with this example right here that already calculated all the individual percentages. So we're looking at 34%. Can't really see that. 34% and 13.5%. So 34 and 34 is 68. That's within 1 standard deviation of the mean. Plus the 13.5. That gets us to 81.5% of the data. So by the empirical rule, we expect about 81.5% of the students to have scored between a 275 and a 350 on this test. All right, there are 2 other methods that can be used in order to determine this answer. Okay, one of the methods we're not going to be doing this year in class. It used to be a very common strategy that you were required to know for the AP exam, but it's been phased out over the years, and it's highly unlikely you're going to have to actually work off of z-tables in order to get the scores, in order to get this type of answer. So in the interest of time and our lack thereof due to our COVID environment here, we're not going to be covering this. The very last slide of this PowerPoint has links to some pretty good Khan Academy videos. If you are interested in terms of how it works to solve these by using Z-tables. You can follow those links, and there's lots of cool stuff to see in there, but we're not going to really worry about that this year. We're either going to be using the empirical rule, which is right here, or we're going to be using one of the advanced features of our calculator, the normal CDF function. All right, quit out of that. All right, in the distributions menu, which is the second function above vars, there's a normal PDF and normal CDF. Okay, normal PDF is used for graphing purposes that we will not be addressing in this particular class. We're never going to use normal PDF. The only one we're going to use is a normal CDF. Okay, when you choose that function, you're going to have to type in 4 things: a lower bound, an upper bound, a mean, and a standard deviation. So the lower bound for this problem would refer to the 275. The upper bound would refer to the 350. The mean, they told us, is 300. The standard deviation is 25. Click Paste. That brings us to the home screen, which lists it out as we will write that out on paper in a second. Let me try to get this so we can see everything. Okay, so when you write this command, you're going to want to write normal CDF, and then you have to label these numbers. And you're allowed to use the symbols for the mean and standard deviation. Press Enter, and we get, if we go 1 decimal place, 81.9%. All right, so the 81.5 versus 81.9. Clearly, they're not exactly the same number. This is a set of percentages that are for quick mental math purposes. They're very often good enough in certain scenarios. This is better. This is a more accurate number. Okay, next thing I want to mention is by AP rubric, as I had said, you're allowed to state the normal CDF command, list the numbers. That's considered showing work as long as you label what those numbers are. If you just have 81.9 without either using this strategy of sketching a curve or showing this work, it's a naked answer. Naked answers get virtually no credit on AP rubrics. So I already mentioned this. When solving problems using technology such as a graphing calculator, the answers that you will calculate will typically vary from those you get from using Z-tables, which we're not going to be going there, or using the empirical rule. The Z-tables we're not going to be addressing. For us, we're either going to be using the empirical rule or we're going to be using a normal CDF on our calculator. The graphing calculators are working with more precise Z-values than when using the other 2 methods. So you're getting a more precise answer. Okay, being that there are 2 answers that by most AP rubrics are acceptable, you have to show, well, which method are you using? And that's emphasizing, again, you have to show the work. Just a naked answer without a justification or work of why you got it is probably going to get you little or no credit. All right, so running through some examples that will illustrate the different ways this could set up in your calculator. Suppose the average height of 3rd graders is 48 inches with a standard deviation of 4 inches. Find a percentage of students whose heights are between 38 and 50 inches. So just as a quick comparison to using the empirical rule here, that's a pretty poorly drawn normal curve. I apologize for that. The mean is 48. Standard deviation of 4 would put that at 52. Would put this down to 44. Put that down to 40. So between, got to go one more, 36. So between 38 and 50 is somewhere in here to somewhere in there. So the empirical rule is not going to work very well. We can get a rough estimate. We know it would be more than something, less than something, but it wouldn't be very accurate. So this problem is not very appropriate to solve by using the empirical rule. This is one that is much more appropriately done using the normal CDF on your calculator. So, normal CDF, left endpoint or lower bound, right endpoint or upper bound, either one of those phrasings or labels would be fine. Mean standard deviation. So we're interested in between 38 and 50. That's our lower bound, upper bound. The mean and standard deviation are coming from the prompt up top. If it says find a percentage, you should answer that percentage form or convert it to percentage form, about 68.53% of the data. All right, what if it's just a greater than, less than? For example, find a percentage of students whose heights are under 52 inches. Okay, in theory, there is no left bound to the curve. That curve goes on forever infinitely in the left direction, on forever infinitely in the right direction. The area under the curve becomes so small that it's rounding to zero, so for the purposes of answering a question, there's no area under the curve, but in terms of the strict mathematical sense, there is an area that exists. So what you need to do is put in an arbitrarily large negative number, so to speak, in a negative direction, or an arbitrarily large positive number if you're looking on the other end. So less than 52 inches, you're going to put a negative 10 to the 99th, or negative 1,000, or some large enough number in a negative direction. Then the 52, mean standard deviation. The mirror image to that guy, find a percentage of students whose heights are at least 47 inches tall. So the left bound is 47. There is no actual right bound. We put in an arbitrarily large number, 10 to the 99th, 48, 4. The 10 to the 99th, negative 10 to the 99th, by the way, are the largest numbers the calculator typically accepts without getting angry with an error message. It's the largest easy number to type in. All right, next example. Suppose that when Tiger Woods hits his driver, the distance the ball travels follows a normal distribution with a mean of 304 yards and a standard deviation of 8 yards. What percent of Tiger's drives travel at least 290 yards? So the lower bound is the 290. The upper bound for this particular problem, they just put 100,000. It's an arbitrarily large number, large enough where, whether it's that or 10 to the 99th, or probably if you put it 600 yards, it would probably give you the same area. Mean standard deviation. So about 96% of Tiger Woods' drives on the range travel at least 290 yards. All right, here's one of the drawbacks of using a density curve in order to answer these questions. You lose the ability to find an exact 290. If you're working with area under a curve, one particular x value doesn't have area above it. You have to have something that has a base with a lower bound and an upper bound. So using a normal distribution in order to find out what proportion of Tiger Woods' drives go exactly 290 yards isn't feasible. It doesn't work. Okay, there is no area under the normal density curve over the point 290. So the answer to our question based on a normal model is 0. Tiger Woods' actual data may contain a drive that went exactly 290, up to the precision of the measuring device. The normal distribution is just an easy-to-use approximation, not a description of every detail of the data. Okay, here's another thing. The areas under the curve, x greater than or equal to 290, x greater than 290, are the same. According to the normal distribution model, the proportion of Tiger's drives that go at least 290 is the same as the proportion that go more than 290. So the actual endpoint values, although in the real world actual raw data may make a difference, using a density curve, particularly a normal curve in this case, is not going to change the answer. Whether it's greater than or equal to 290 or just 290, it's the same answer either way. And again, that's another drawback of using this particular strategy. The strategy is not perfect. It works really well for a lot of problems, but it doesn't work perfectly for all problems. All right, in statistics, we often need to distinguish values that are typical or usual from values that are unusual. By applying the empirical rule, we find that about 95% of all values from a normal distribution lie within 2 standard deviations of the mean. That implies, or this implies, that among all values, 5% lie more than 2 standard deviations away from the mean. Okay, we can use this property to identify values that are relatively unusual. So if you're looking at a problem that can be modeled with a normal curve or a normal distribution, and you're asked to identify an unusual event or an unusual something, whatever fits the context of the problem, being more than 2 standard deviations away from the mean is an acceptable parameter in order to make that decision. So, for example, a recent study found that credit card debt for college students is normally distributed with a mean of $4,100 and a standard deviation of 800. Would it be unusual to randomly select a college student with $5,800 in credit card debt? So, from above, we just got done saying an event to be classified as unusual in a normal distribution if it is more 2 standard deviations away from the mean. So they said the mean was 4,800. 2 standard deviations would be 2 plus 800. We're looking at something in the positive direction. So the mean plus 2 standard deviation puts us at 5,700. So on the high end, that would be the cutoff for determining is an event unusual or not. Any credit card debt greater than 5,700 can be considered unusual. Since 5,800 is greater than 5,700, we can classify that as unusual. All right, now we're going to reverse the order, or reverse the direction, rather, of the order of the question. Scores for a civil service exam are normally distributed with a mean of 75 and a standard deviation of 6.5. To be eligible for civil service employment, you must score in the top 5%. What is the lowest score you can earn and still be eligible for employment? All right, depending on what version of a TI-83, 84 you have, there are 2 potential set of keystrokes that you need to do. The first one is going to be if you have an older operating system. If you have one of the bigger, boxier 83s or 84s, there's a chance that it's an older operating system. There's also a chance a newer operating system. They can be updated, so just because of what it looks like doesn't guarantee the operating system. If you have one of these thin ones that look like our class set ones, there's a really good chance that it's an older operating system. The bigger, boxier ones are hit or miss. So, if you're using an older operating system, they only work on area to the left. So if you want to be in the top 5%, you want to be in the 95th percentile, meaning you want to calculate what X value is necessary to get 95% of the area to the left of the normal curve representing this situation. So what we're going to be doing is going to the same distribution menu, which is second vars, and right below normal CDF is inverse norm. Okay, when you're using inverse norm on a newer calculator here, you get to specify left, center, or right. The older operating systems, it's always left. That option isn't there. So when you type in area, mean, and standard deviation, it has to correspond to a particular area to the left of the curve. So back to this problem, we need to get 95% of the area to the left of the curve. So we have to type in 0.95. And this is in a situation where the mean is 75 and the standard deviation is 0.65. And that's just coming from the information above. Left, paste, and something doesn't look right here because that's a different answer than what is on this page. So something is not quite right here. 75. Oop, I typed in 6.5 instead of 0.65. So you're looking at, if we're going to round to the nearest whole number, you need about an 86 on this test to place in the top 5%, which means that you're at the point of the curve where 95% of the curve is to the left, 5% of the curve is to the right. All right, now with the newer operating system, as you saw when I typed in that, we don't have to do area to the left. We can do area to the left, we can do area in the center, or we can do area to the right. So if we just want to use that 5% as it appears in the problem, we can type in 0.05, same mean, standard deviation, that was wrong, 6.5, and then choose right area instead of left area, and hit paste. Enter, and you see we get the exact same number. So whether you're finding 95% of the area to the left or 5% of the area to the right, if it's a normal curve, it's the same answer. So if you are using a calculator from the class set, you have those options. If you're using your own personal graphing calculator and it doesn't have one of the newer operating systems that allows you to specify left, right, center, then you have to work off of area to the left. That is just the nature of your calculator, and that's what you're going to have to get used to. All right, some more practice. Clarifying some of this stuff, connecting it back to what we started with. The length of time employees have worked at a corporation is normally distributed with a mean of 11.2 years and a standard deviation of 2.1 years. Okay, what percent of the employees have worked at this corporation for more than 13 years? All right, if you are looking for what percent of something fits a particular category, you're using the normal CDF. Okay, the normal CDF doesn't matter whether you have an older operating system or a newer operating system. What you have to type in is identical for both. It's lower bound, upper bound, mean, standard deviation. Now, in the interest of space on this particular page, these numbers aren't labeled, but for a free response question, you want to make sure that those get labels to them. Okay, in a company cutback, the lowest 10% in seniority are laid off. What is the maximum length of time an employee could have worked and still be laid off? So what does it take to be in the lowest 10% of this particular data set? Okay, when you're given a percentage and you want to know a particular number, that's when you're going to use the inverse norm. So the older operating system, you don't specify the tail at the end. It's always just going to be left. So lower bound is, I'm sorry, there is no lower bound. I don't remember, what is the order for this? This is area, mean, standard deviation. So we want 10% of the curve to the left in a situation where the mean is 11.2 and the standard deviation is 2.1, so the cutoff is about 8.5 years. With a newer operating system, you'd have to specify that left, right, center at the end, and you get the same answer. Okay, the weights of bags of baby carrots are normally distributed with a mean of 32 ounces and a standard deviation of 0.36 of an ounce. Bags in the upper 4.5% are too heavy and must be repackaged. What is the most a bag of baby carrots can weigh and not need to be repackaged? So if you're working off the older operating system, you have to be working off of area to the left. So 4.5% on the upper end means it's 95.5% on the lower end, the mean and standard deviation. With the newer operating system, if you wanted to use that same percentage, you'd have to specify to the left, or 95.5% to the left is the same as 0.045 to the right. They're going to give you the same answer. Again, know your calculator, whatever it is you're going to be using, get used to those keystrokes. All right, a couple more examples. A fast food restaurant has just installed a new automatic ketchup dispenser for use in preparing its burgers. The amount of ketchup dispensed by the machine follows a normal distribution with a mean of 1.05 ounces and a standard deviation of 0.0 ounces. If the restaurant's goal is to put between 1 and 1.2 ounces of ketchup on each burger, what percent of the time will this happen? So when you're looking for a percentage, given some boundaries, you're using normal CDF. The lower bound is 1. The upper bound is 1.2. The mean and standard deviation, 1.05, 0.08 ounces. There's only one way to type that in your calculator, and you end up getting about 70.36% of the time. All right, suppose that the manager adjusts the machine settings so the mean amount of ketchup dispensed is 1.1 ounces. How much does the machine standard deviation have to be reduced to ensure at least 99% of the restaurant's burgers have between 1 and 1.2 ounces of ketchup on them? So I'm going to sketch a curve to help visualize this. So it's set up so the mean is 1.1 ounces. And we're looking for getting 99% of the data in between 1 and 1.2 ounces. I'll put the 1.0 just so it doesn't look like I forgot to copy something. All right, so if we tried to use inverse norm, it's going to ask us to type in a standard deviation. Well, a standard deviation is what we're looking for. How much does a machine's standard deviation have to be reduced? So we can't use inverse norm just yet. We need to use something else in order to be able to use that inverse norm. So what we're going to have to go back to is our z-score formula. We're going to need to incorporate this into the problem-solving situation. So what I'm going to do is I'm going to get the z-score for that value right there. Okay, so that particular value is 1.2, and that's in a distribution where the mean is 1.1 and the standard deviation is what we're looking for. All right, so we hit another roadblock. We still got to get that z-score. So how are we going to get that z-score? What we're going to do is use a standard normal curve. What does it take to get let me clear this stuff out. I'm sorry, I got distracted by these numbers. Oh, it's not letting me clear these. I thought we could clear them out. If 99% of the data is between here and here, it means 0.5% is to the right and 0.5% is to the left. So this value right here has to have a z-score that gets 99.5% of the curve to the left. So what we're going to do is 0.995. The mean, we're going to put in 0. And the standard deviation, we're going to put in 1. And we're going to choose left, and I'm going to hit paste. So that's a z-score of 3 decimal places. 2.576. So that's what we can use right there. In any normal curve, in order to get 99.5% of the data to the left, it has to be a z-score of 2.576. That'll correspond to an actual value of 1.2 ounces. So now, those two pair up, as in that's the z-score that goes with that particular value. That's the mean, and now we can solve for the standard deviation. So 1.2 minus 1.1, that's 0.1. Multiply both sides by sigma. Divide by that. 0.1 divided by 2.576. We get a sigma of about 0.039, I guess. I think 4 decimal places might be a little extreme. So, if we have the mean set at 0.1, and we want 99% of the ketchup squirtants here to land between 1 and 1.2, we need a standard deviation of 0.039 ounces. And the key to this problem that we didn't have to do with the previous easier ones is, in order to use the advanced features of the calculator here, we had to get a z-score for just a standard normal curve. What if it's a mean 0 and a standard deviation of 1? That would be 2.576. 1.2 is 2.576 standard deviations to the right of the mean of 1.1. All right. Next slide here. Chebyshev's inequality. I'm not sure if I pronounced it right, but no matter how you decide to pronounce it, it's fun to try to say. Okay, the rule of 68, 95, 99.7 applies only to normal distributions. Is there a similar rule that will apply to any distribution? Well, sort of. A result, known as Chebyshev's inequality, says that in any distribution, the proportion of observations falling within k standard deviations of the mean is at least this guy right here. So 2 standard deviations away from the mean would be 1 minus 1 over 2 squared, which would be 1 minus a half squared. 1 minus a half squared is a fourth, or 3/4. So in any distribution, based on this guy's inequality, 3/4 or 75% of the observations are within 2 standard deviations of the mean. For normal distributions, we know that this proportion is much higher than 0.75. In fact, it is 0.95. This is the lower bound. It has to be at least 75%. In normal distributions, actually 95%. Okay. Chebyshev's inequality is an interesting result and is addressed in most introductory stat classes. It may be used in a free response on the AP exam, but it is not required. As such, it will not be required for this class. Okay, it pops up every now and again. It's not a main part of the book because it's not part of the main part of AP statistics curriculum, but it is something where if they gave you this formula and asked you to apply it, then you would be expected to know enough in order to be able to apply it. But you wouldn't have to know it by name. You wouldn't have to have the formula memorized. If given the formula with the name, you'd be expected to be able to use it, for example, like we did here. But it's not anything that is going to be stressed. It is stressed, though, in many introductory statistics classes, just not the one that we're in right now. All right, the last slide here. As I mentioned, all of these problems that we did today can be solved by working off of z-tables. Z-tables have been significantly de-emphasized on the AP exam. It's highly unlikely that you're going to see a question where you'd have to use a z-table. If so, maybe it would be one obscure multiple choice question out of 40, in which case, so be it. We're not going to spend the, potentially, hours going over all the different ways you could use z-tables. If you're interested in it and you want to learn more, Khan Academy's got some really good videos. I linked them all here. Check it out on your own. Other than that, we're not going to be dealing with it at this moment in time.